Hello everyone, and welcome to Soil Moisture 301, Hydraulic Conductivity, Why You Need It, How to Measure It. Today's presentation will be 20 minutes, followed by 10 minutes of Q&A with our presenter Leo Rivera, whom I'll introduce in just a moment. But before we start, we have a couple of housekeeping items. First, we want this to be interactive, so we encourage you to submit any and all questions in the questions pane. We'll keep track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, no problem. We're recording the webinar and we'll send around the recording via email within the next 3 to 5 business days. All right, let's get started. Today we'll hear from Leo Rivera, who will discuss hydraulic conductivity and how to better understand water movement through soil. Leo operates as a research scientist and hydrology product manager here at Meter. He earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also got his master's degree in soil science. There he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in Meter's hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. So without further ado, I'll hand it over to Leo to get us started.
All right, thank you everyone for attending today's virtual seminar, Soil Moisture 301. Hydraulic conductivity is one of my favorite topics to talk about, so I'm really looking forward to this seminar today. So just a little introduction about myself. My background is in soil physics and pedology. This is what I studied, and this is what most of my research is focused around. Throughout my time here at Meter and throughout my graduate studies, I've gained 12 years of experience measuring and interpreting soil hydraulic properties and measuring soil moisture release curves. I've had many conversations with researchers looking at their data, looking at different methods and trying to better interpret their what their soil hydraulic properties measurements mean and trying to come up with new ways to approach different topics. So I've had a lot of fun over the past 12 years looking at these various topics and talking with researchers about this. So I'm actually going to jump back into this slide that we finished on in Soil Moisture 201. And in the past 2 virtual seminars, the focus has really been on the state of water and soil. So we've looked at water content and water potential. But if you really want to get the big picture and fully understand ecosystem fluxes, you need to know more. And one of those key parameters is hydraulic conductivity, because really that is the governing factor in how water is going to move throughout the vadose and through soil, and it's really going to control how the flux of water within the ecosystem. And so it's an important parameter to measure, and today we're going to try and focus a little more on that. So here are some of the goals from today's virtual seminar. I really hope you come away with a better understanding of what hydraulic conductivity is and what impacts hydraulic conductivity. We're also going to try and give you some more knowledge on some of the different hydraulic conductivity measurement methods and how they might best suit your research goals. We're also going to cover some applications of hydraulic conductivity and show some of the ways we've used it and just some of the ways it's been used to understand different problems within the environment. And then we're going to briefly cover how this ties into soil health. So why do we even care about hydraulic conductivity? Well, it impacts almost everything soil is used for. It impacts crop production because it's going to impact how well water is able to infiltrate into the soil to be stored later for use. This is especially important here in the Palouse where we're located. It also is going to impact how water is redistributed through the soil profile for crop use. It's also going to impact irrigation and drainage. So it's going to impact how fast we can irrigate and how the water is going to infiltrate into the soil. But also we have soils where we're going to have drainage issues because they have low hydraulic conductivity. And so this is another important thing that needs to be understood. Hydraulic conductivity is obviously a really important factor in hydrology in both native and urban environments. It's one of those main factors that affects how water is going to run off through a watershed and how urbanization is going to affect that and how that impacts downstream flows. And in turn, it's also going to impact stormwater system design as we try to better mitigate urban runoff and better control that so we're not having big flood events, and so we can better design our stormwater systems, and we need to understand both the native soils and the constructed soils. It's also important in landfill performance, ensuring that our landfills are able to prevent water from infiltrating into the landfill, which can there in turn lead to contaminants moving throughout the soil and potentially moving into groundwater, which is obviously a big problem. And hydraulic conductivity is being used to help us better understand soil health, and we'll briefly cover that later in the virtual seminar. So what is hydraulic conductivity? Hydraulic conductivity is a measure of the ability of a porous medium, in this case we're talking about soil, to transmit water either in saturated or unsaturated conditions. And what affects hydraulic conductivity? What actually determines the hydraulic conductivity of our soil? Well, one of the first things we're going to think about, of course, is soil texture. What is our sand, silt, and clay fractions, and the makeup there? And that's typically the first thing we think about when we're thinking about hydraulic conductivity. But there are other factors that also play a huge role, and in some cases play a bigger role than soil texture. Soil structure, in my opinion, is one of the most important factors to think about when we're looking at hydraulic conductivity. And I'll show a slide here shortly that kind of better visualizes that. Biopores are also obviously going to have a big impact. So decaying root channels, wormholes from good worm activity, all of those things are going to impact hydraulic conductivity. And compaction and bulk density obviously are going to have an impact as we become more compacted and we have higher increased bulk densities. We're going to see changes and decreases in hydraulic conductivity. Other things that we know throughout the literature is that antecedent soil moisture, so what the water content is at the beginning, can have an impact on what the hydraulic conductivity is. This is especially important in shrink swell soils. And then water potential is obviously important in unsaturated hydraulic conductivity as well, because that's really the main driving factor that's moving water in unsaturated conditions is the water potential gradient. So as we know, a porous medium can be saturated or unsaturated. And depending on the condition or the state that it's at, it's going to affect what the hydraulic conductivity is. So here we're looking at a graph of 3 different soil types. We have a well-structured clayey soil, a structureless sandy soil, and a poorly structured clayey soil. On the y-axis, we have hydraulic conductivity, and on the x-axis, we have the water potential. And what we see is as the water potential decreases, as the soil becomes drier, the hydraulic conductivity decreases. And we can see what happens with the 3 different soil types as it gets drier. Eventually they may cross each other, so they will have differences depending on the state that they're at. But I think the most important thing to look at here is the impact of structure. What we see is that a well-structured clay soil can have significantly higher hydraulic conductivities at and near saturation than that of the poorly structured clay soil. And in some cases, it is actually higher than the sandy soil, again, showing that we can't just rely on soil texture to estimate hydraulic conductivity. And again, just highlighting the impact of structure and why that's important. So when we're thinking about saturated hydraulic conductivity, all of the pores that are in the soil that are able to contribute are contributing to the flux of the soil. And in saturated conditions, we've really gotten rid of the matrix forces. So as the soil becomes saturated, the impact of matrix forces becomes negligible. And really, saturated hydraulic conductivity is primarily driven by gravitational forces. But in many cases, this is a less common state of flow in soil. How many of our sites are always saturated? They're not. And so when we think about what's happening is they're typically existing in unsaturated conditions. But saturated hydraulic conductivity is important because it really comes into play in many applications. So one of those main applications that we think about when we're thinking about saturated hydraulic conductivity is runoff modeling, of course. So when we're having a big rainstorm event coming in, as the soil becomes saturated, what is its limiting? How is it going to limit the rate at which the water can infiltrate into the soil, and then eventually resulting in more runoff? And so this is really important in measuring water flow in watersheds and understanding potentials for erosion and those types of things. It's also an important measurement for groundwater flow, just to better understand how water is going to move throughout the groundwater table. And also in green infrastructure assessment, hydraulic conductivity is really important in making sure that we design our rain gardens and our bioswales and all these things to be able to properly infiltrate water that's coming off of, say, a parking infrastructure to help us do a better job of mitigating urban runoff. Now, when we're thinking about unsaturated hydraulic conductivity, one thing to understand, and what we saw on that curve, is it varies depending on the pore sizes that are able to contribute to the water fluxes. So as we become drier, as we approach lower water potentials, the larger pores are no longer able to contribute to the movement of the water throughout the soil. And because of this, we see lower hydraulic conductivities, which makes sense. And also, with unsaturated hydraulic conductivity, the main driving factor is our matrix forces. That's the main thing that's driving water movement through the soil. And in many cases, this is the most common state of flow in soil. So if we're trying to understand how water is moving throughout the vadose zone and in the profile, this is really where unsaturated hydraulic conductivity comes into play. When we're trying to better understand vadose zone hydrology and how water is going to move, even from, so when we're thinking about groundwater exchange with the unsaturated zone and how it's rising due to capillary rise, and when we're looking at stream interactions with the unsaturated zone, and also when we're thinking about hyporheic exchange as the plants are pulling up the water from that stream soil interface, the unsaturated hydraulic conductivity really plays a big role here. So, how can we measure hydraulic conductivity? Well, the first thing we typically think about when measuring hydraulic conductivity are field measurements. And there are several options for measuring hydraulic conductivity in the field. So when we're thinking about saturated hydraulic conductivity, one of the first main approaches is actually to take a ring and insert that ring into the soil and measure the water flow into that ring, either using a constant head or a falling head approach. And what we're looking for is we're going to measure for when the infiltration rate reaches a steady state flux. That means we've started to fill all of those pores and the soil has become saturated, and we're getting that steady state measurement. And so now we're going to be able to actually start measuring saturated hydraulic conductivity. And with those ring measurements, we also have three-dimensional flow away from the ring. So if we're wanting to get to saturated hydraulic conductivity, we have to make corrections for three-dimensional flow based on the matrix forces that soil is able to exert. We usually refer to that as the alpha value, or the soil macroscopic capillary length factor, which is related to the sorptivity of the soil. And so with these ring style infiltrometers, we have to make that correction. Traditionally, with single and double ring infiltrometers, we usually will use a table to estimate that property for the soil that we're measuring in, and then we'll put that into the equations afterwards to do correction for three-dimensional flow. Now, one of the potential issues with this approach is that if you use the wrong value, you can significantly overestimate or underestimate your hydraulic conductivity. So you do have to be careful when you're selecting the alpha value. With the Saturo, or the dual head infiltrometer, what we do is we actually infiltrate water using two different pressure heads from a single ring infiltrometer, using a constant head at both pressure heads. And what that allows us to do is actually go in and directly estimate what that sorptivity is of the soil, or get at that alpha value. So it actually allows us to do this correction for three-dimensional flow automatically. So there is an advantage of using the dual head approach. Now, another approach for saturated hydraulic conductivity in the field is a borehole measurement method. And so typically what that involves is augering a borehole in the soil down to your desired depth that you want to measure at, and then using a Marriott bubbler, as you see in this image here, to control a constant head within that borehole and measure the infiltration rate into the borehole. And again, we're looking for that steady state value. The advantage of the borehole approach is it allows us to get down to a deeper depth that we typically wouldn't be able to do with the ring style infiltrometer. But one of the disadvantages of this borehole approach is when you're augering a hole, you run the risk of smearing pores and closing them off. So you may wind up underestimating your hydraulic conductivity with this approach. But it's the only approach that really makes it easy to get down to a deeper depth. Now, when you compare the ring methods versus the borehole methods, one of the other pros and cons between the two is with the borehole, because it's a smaller borehole, we're not covering as large of an area. So we may see some issues with spatial variability. Whereas with the ring style infiltrometer, we can measure over a larger area, which is going to help us encompass some of that spatial variability. So something you have to think about when you're looking at those different methods. Now, when we're thinking about unsaturated hydraulic conductivity, the most common method that's used to measure unsaturated hydraulic conductivity in the field is a tension infiltrometer. And essentially what that involves is you're going to have a porous disc or plate that is going to be connected to a water reservoir that is controlled with a Marriott bubbler. And what that allows us to do is actually control the suction to that porous plate. And in turn, we can limit which pores are able to contribute to the flux. And that actually allows us to get measurements at different tensions of to help us better measure that unsaturated hydraulic conductivity curve. Now, with this tension, with the tension infiltrometer, just like with the single, double ring, and borehole, we do have to do corrections through three-dimensional flow. And so again, we're having to estimate some of these soil properties to better correct for three-dimensional flow. But one of the nice things about a tension infiltrometer and about doing unsaturated hydraulic conductivity is there's less of an issue with spatial variability because we're getting away from the structural effects and more so just looking at the impact of the bulk density and the soil texture. And we don't see as much of an issue with spatial variability when measuring unsaturated hydraulic conductivity. Now in the lab, there are a few main approaches that we use to measure saturated and unsaturated hydraulic conductivity. All of these approaches are going to involve taking a core sample from the field and bringing it back to do your measurements. With saturated hydraulic conductivity, what we're doing, whether it's with a KSAT or a flow cell device, we're infiltrating water at either a constant head or a falling head, and measuring either the inflow into the sample and looking for that steady state value, or we're measuring the outflow and again looking for that steady state value to get at the saturated hydraulic conductivity. With the KSAT versus the flow cell device, one of the main advantages of the KSAT is that it's a fully automated device, so there's really no need to set up a measurement for the outflow or the inflow. It's just set up and ready to go. With a flow cell device, typically you're going to have to customize your setup and get it built and ready for you. So it's just a little more work into getting that setup going. With unsaturated hydraulic conductivity, again, we're taking a core sample, and there are two kind of differing approaches here. With a flow cell setup with tensiometers, what we're doing is we're infiltrating water through the core sample, but instead we're actually infiltrating the water at a set flow rate. And what we're doing is monitoring the tensiometers to see when they equilibrate with each other. And we're measuring the outflow at that time. And what that allows us to do is one, we're getting at the unsaturated hydraulic conductivity because we know what the water potential is and we know the flow rate that's occurring. And what we can do is we can step this at different flow rates. And this allows us to actually get multiple points on the unsaturated hydraulic conductivity curve. And it also allows us to get the soil moisture release curve. So this is a little more manual, but it's a really nice approach. With the high prop, instead, we're actually starting with a saturated core sample, and we're using what's called the Windschindler evaporation method. And we're evaporating water from the surface of that core, and we're measuring the change in water content, so we're getting the evaporation rate, and then we're measuring the change in water potential at two different points within the core. And what that gives us is we get a gradient we get a difference in the change in water potential at those 2 points, along with the change in water content. We're able to calculate the unsaturated hydraulic conductivity based on Darcy's law. Now, a limitation of this method is near saturation. We don't have enough of a gradient between the two tensiometers to measure unsaturated hydraulic conductivity. So depending on the point that you're at on the soil type, you may see a little bit of a gap there when you're near saturation. So one of the common questions that we get and a common issue that people run into and we see in the literature is, how do lab and field measurements compare? Well, when we're thinking about field measurements, it's really a complete soil interaction. We're measuring how the water's moving through this entire soil profile to an extent. And really, one of the main things that's controlling that is whichever layer is the most limiting layer. But this really gives us the best idea of how things are interacting in the field. When we think of lab measurements, we're really taking a single point assessment. So we're taking points at different points we're taking samples at different points within the profile and bringing them back to the lab and measuring their properties there. The advantage of lab measurements is we really get to isolate the sample, and we don't have any effects of three-dimensional flow. So really we can do a better job of getting at the intrinsic soil properties versus field measurements where we're just kind of looking at the total soil interaction. But some of the issues we run into is saturated and unsaturated lab measurements almost never compare very well with field measurements. And one of those reasons is, let's just say I took a core sample that had an old decaying root channel in it. And in the field, that root channel is eventually going to close off. But in this core sample, if I take it at the right spot, it's going to be a huge open-ended pore that's going to result in a much higher measurement of hydraulic conductivity than what we would see in the field. So it actually becomes really hard to compare these two methods. I think they both have their place, and it really just depends on what your research goals are and what you're trying to understand. So what can hydraulic conductivity tell us? So I'm going to bring back up this example of water availability. So when we're thinking of water availability, we typically think about field capacity and permanent wilting point. But are these the two main factors that really limit water availability, or are there other things that can impact the availability of water to plants? So let's take, for example, a soilless medium. So here we have a soilless media, we call it the McCorkle sample, that's made up primarily of a mixture of bark and then other materials. And with that mixture, we have a lot of fine pores within the bark and then larger pores around the structure that's made as the material comes together. With this material, what we were seeing was plants were beginning to stress at minus 10 kilopascals water potential. That's still very wet. And so we didn't quite understand why the plants were beginning to stress at this point. And so one of the first things we did is we actually measured the soil moisture release curve of this sample. And the first thing that stood out was, well, this has a bimodal soil moisture release curve. And what does that tell us? Well, when we think about soils, typically we have well-graded soils that have a good mixture of different pore sizes or uniformly graded soils. But with a material like this, what this curve is telling us is that we actually have a gap-graded substrate. So we have a good amount of larger pores and a good amount of smaller pores, but we're missing those intermediate pores, which is resulting in this bimodal curve. And what we noticed was that this was occurring right around 10 kPa, right around where we're starting to see the plants beginning to stress. So what is actually causing the stress and why are we seeing these issues? Well, luckily, because we measured the soil moisture release curve with the hypocop, we also had the unsaturated hydraulic conductivity curve. And what we found was that this McCorkle sample had a much lower unsaturated hydraulic conductivity than we expected at this point, much lower than typical soils, and just really a pretty low hydraulic conductivity at minus 10 kPa. So what is this doing? What's actually happening? Well, it's actually limiting the redistribution of water throughout the substrate. And because of this, as the plant's uptaking the water, we're actually getting the interface right around the roots. They're actually experiencing a much lower water potential than we're actually measuring in the substrate because we're not getting that redistribution of water due to those matrix potential gradients that you would normally see in most materials. And so what we found was that it was really unsaturated hydraulic conductivity that was one of the limiting factors here for this material. What are some other applications? Well, this is based on some research that I did throughout my graduate studies. And we were looking at the impacts of land use and landscape position on hydraulic properties of the same soil type. In this case, it was a Houston black soil. And we looked at 3 different land uses: the tall grass native prairie, an improved pasture, and a conventional tillage field that were in a corn wheat rotation. And what's great is we were able to access a site that's been in the same land use for over 60 years. And this proved to be a great test bed for evaluating the impacts of these land uses. And so what we did is first thing we did is we actually took a bulk, we did an EM38 survey, and we're able to get a bulk EC map for the field. And this allowed us to establish some zones of variability. Even though this field is all mapped as the same soil type, there were still zones of variability. So we measured at the zones of variability and within the different landscape positions, so the summit, the hill slope, and the foot slope. And then, of course, we did the same thing at the 2 other fields. And what we found when we finished all of these measurements was that, one, we saw an impact on the measurements from landscape position. So as we moved across the summit, the back slope, and the foot slope, we saw changes in the soil hydraulic properties, which makes sense because of the Katina effect and how water is moving throughout the hill slope and how that moves nutrients and how that moves clay and fine materials. And so this was impacting the soil hydraulic properties. We also saw differences in land use. One thing I would like to point out is when we made the measurements in the conventional tillage field, it was shortly after they had come through and plowed. And what we would expect to see and what we've seen in future work is that as the soil has had time to consolidate, the hydraulic conductivity becomes much lower in this field, because we've essentially gone through and destroyed any of the pore structures that can have a huge impact, have a much larger impact on the soil's ability to infiltrate water. So now we'll kind of tie this into soil health. So according to the Soil Health Institute, 19 measurements are considered effective indicators of soil health. Those measurements are broken down into 3 main categories. We're looking at chemical indicators of soil health, physical indicators of soil health, and biological indicators. And one of those physical indicators is infiltration rate. So they're using that infiltration rate to help assess soil health and factors that are improving soil health. So what are we actually measuring when we're measuring infiltration rate that is telling us that we have healthier soils? Well, one of those things obviously is improved soil structure. So a higher infiltration rate tells us that our soil structure is stronger and better. It also means that the aggregate stability is better. It's also telling us that we have more biopores from decaying root channels. And we also have increased biological activity. So we have more worm activity and we have more fungal activity, which is of course leading to better soil structure because it's helping with the aggregate stability. So all of these things are indicators that we have a much healthier soil, which will lead to a more long-term productive field. And so this is some of the work that's being done, and this is one of the ways that infiltration or hydraulic conductivity is being used to help us assess soil health. So just to recap, just to kind of wrap it up of what we've discussed over the past 3 virtual seminars. So we're kind of wrapping up the soil moisture series. We had Soil Moisture 101, where we discussed the basics of water content and water potential. In Soil Moisture 201, we took a deeper look at water potential and what it means. And today in Soil Moisture 301, we had more of a focus on measuring fluxes and hydraulic conductivity and hopefully bringing everything together to help us better understand how we can measure the big picture. Now in the future, in some of our future virtual seminars, we hope to cover how the measurements are made and how to make the best possible measurements. We'll move on to questions.
Awesome, thanks, Leo. So it looks like we probably have a couple minutes here to take some questions from the audience. And thanks again to everyone who has sent in their questions already. There's still time to submit some here in the last couple minutes. And we'll get to as many as we can before we finish here. Also, if your question is not answered right now while we're doing this live, we do have them recorded and we'll be able to send you an email with those questions answered. All right, so let's check this out and see what questions we've got here. So here's one. If field and lab measurements are different, is it recommended to complete the water content curve obtained with the hyprop in the lab with field measurements?
So that's a really good question. This is a really hard question to answer because I think it really depends again on what your research goals are. If ultimately your goal is to understand individual types of soil, so if we're trying to look at a B horizon of a soil type and understand what its intrinsic soil properties are, then I think the better approach is to take lab measurements, is to bring a core sample back, do your lab measurements. Obviously, you're going to have better control that way, and conduct it in that approach. But if your goal is to understand interactions in the field and what we're going to expect to see in the field, then I think the better approach is still to do the field measurements. So ultimately, it really depends on your research goals and how you want to approach those measurements.
Okay. How about this one here? What is more significant to measure for irrigation, saturated or unsaturated conductivity?
So I think saturated hydraulic conductivity is more important in this factor because one of the things we need to understand is what's going to be the most limiting. Because as the soil is, as we begin irrigating and the soil is wetting up, we have those matrix forces that are help pull the water into the soil. And really what's going to limit things is as we approach saturation near the surface, we may get ponding of water, which could ultimately lead to runoff. And so that's really going to affect what your irrigation rates can be. So I think ultimately saturated hydraulic conductivity is more important in this case.
All right, maybe we'll do probably two more here. How about, here's one. I don't really understand why hydraulic conductivity in near saturation is so unreliable for higher suction.
So hopefully I'm understanding this question right. So hydraulic conductivity near saturation, it's not that it's unreliable. Some of the different measurement methods have issues making that measurement. So we talked about two approaches, the flow cell versus the hyprop. The hyprop struggles near saturation to make the unsaturated hydraulic conductivity measurement because we just don't have enough of a difference between the two tensiometers to really measure that. With the flow cell approach, we actually can do a better job of measuring unsaturated hydraulic conductivity near saturation. So it really just depends on the approach that you take.
Okay, I think we've got last one here. How about this one? So this question is about soil with rocky fragments. It's a very common soil type. How do we deal with that?
Yeah, that is a very common issue that we run into. And it is probably one of the hardest things to deal with, especially depending on the size of the rock fragments. There's a couple approaches you could take. When using a ring infiltrometer, you just have to be really careful. If you can do a good job of installing around the rock fragments without hitting one and driving it into the ground, then you can use that approach. Another option actually might be to take either a core sample or to do a borehole approach, because with the borehole approach, we can take a smaller area and auger down and try and avoid those rock fragments a little bit better. So it really depends on what, it really depends on how bad the rock fragments are and if you can avoid them. But that is a really tricky situation to measure in.
All right. Thanks again, Leo. That's going to wrap it up for us today. Thanks again for joining us. We hope you enjoyed this discussion. And again, thank you for such great questions. If your question was not answered, just want to remind you that we will be sending out emails with answers to your questions, either from Leo himself or one of our other experts here. Also, please consider answering the short survey that will appear after this webinar is finished to tell us what types of webinars you'd like to see in the future. And look for the recording of today's presentation in your email, and stay tuned for future meter webinars. Have a great day.